This is section 7.2, the inverse trig functions continued. So last time when we were solving, we were working with trig functions that were identical. In other words, they were our inverses of each other. So we had sine with inverse sine, or cosine with inverse cosine, or tangent with inverse tangent. Today we're going to be adding a new twist to the problem. Remember that sine, or inverse sine, can only use quadrants 1 and 4. Inverse cosine used quadrants 1 and 2, and inverse tangent used quadrants 1 and 4. Well, since these both use the same quadrants, this problem's really not going to be any more difficult than any other problem we've worked with. When we look at this, we have to recognize, though, that they're telling me the tangent value. This is the ratio. I need the angle so that I can find the sine value of that angle. The only way to get an angle like that, if I don't have a graphing calculator and I want an exact value, so no graphing calculator can be used, would be to draw a triangle in the correct quadrant. Well, the inverse tangent of 1/2 means that my tangent value is positive, and of these two quadrants, the tangent value is positive in quadrant 1. So I'm going to draw my triangle in quadrant 1. The tangent value, remember, is y over x, or opposite over opposite over adjacent. And so y over x means this value would be 1, the x value would be 2, and my theta is right there. Now, I know the sine value of theta will be opposite over hypotenuse. So if I can find the hypotenuse value, this just becomes a problem of filling in opposite over hypotenuse. So 2 squared plus 1 squared, I'm going to use x squared plus y squared equals r squared, or a squared plus b squared equals c squared, your choice. So 4 plus 1 equals r squared, which means that r is the square root of 5. If r is the square root of 5, then the sine of the inverse tangent of 1/2 would equal 1 over root 5. Now remember, we need to rationalize our answer, so our answer is root 5 over 5. That fits because it's positive, and the sine of any angle in quadrant 1 would have to be positive. All right, let's look at problem example 2. Find the exact value of cosine of sine of -1/3. Now, in this particular problem, sine value of -1/3 is in quadrant 4. So I'm going to draw quadrant 4, okay, and that's going to be opposite, so -1 over hypotenuse. And remember, the negative goes with the down, and the radius is always positive. So I need this x value, this adjacent value, so that I can find the cosine. Now, I know some of you are looking at this and saying, wait a minute, sine is in quadrants 1 and 4, but cosine is in quadrants 1 and 2. But where is cosine positive? In quadrant 1. And cosine of quadrant 1 matches cosine of quadrant 2. So this is going to work out okay, even though, because we're not looking for the angle, we are looking for the cosine value. And so even though this is in quadrant 4, this worked out, telling me which quadrant to put it in, and the cosine value matches quadrant 1's and quadrant 4. So 9, once again, I'm going to do x squared plus y squared equals r squared, only this time I'm going to know x, I don't know x squared, plus 1 equals 9. So x squared equals 8, x is equal to 2 root 2. Now I need it to be positive because it's in the positive direction, and so my cosine value is going to be 2 root 2 over 3. Problem done. The last problem that we have is tangent and cosine. Now, cosine is negative in quadrant 2. So I'm going to draw my triangle in quadrant 2. And then you have to ask yourself, can I find a tangent value in quadrant 2? Yes, I can. It's not a restriction. We don't restrict tangent because we have to. We restrict tangent only when we need to do the inverse. So cosine is adjacent, that's -1, the x value, over the radius, or hypotenuse. So I've got -1 and 3. Once again, x squared plus y squared equals r squared, only it's 1 plus y squared equals 9. So y squared equals 8. And y is positive in that quadrant. y is going to be a positive value in that quadrant. So y is equal to 2 root 2. The tangent value is y over x, so that's equal to 2 root 2 over negative 1, which simplifies to negative 2 root 2. And tangent is negative in quadrant 2, so that works out, and it's all good. So the slightly tricky part of this problem is that we're going to be adding the inverses of secant, cosecant, and cotangent. Now don't worry, I'm not going to ask you to graph these, but I do need you to recognize that this is the graph right here of secant. And looking at the graph of secant, do you see that it's not 1 to 1 again? This graph is not 1 to 1. Well, the only way to make it 1 to 1, if I were to break it right here at the asymptotes, that's not 1 to 1. If I break it there at the asymptotes, it's not 1 to 1. So the only way to do this problem is to break it here. We're going to break it from 0 to pi. So the domain we're going to use for secant is 0 to pi. What else did we use from 0 to pi? Cosine. Well, that makes sense because secant of theta is equal to 1 over cosine of theta, and the secant inverse is related to the cosine inverse as well, just a little differently than you think. We'll come back to that in a minute. Looking at this graph, this is cosecant. Once again, to break this so that we can see full sections, it's not going to be where the asymptotes occur, but right there instead. So I'm going to not look at this, and I'm only going to look in between these two sections. That gives me a full coverage of cosecant, and it allows me to have every y value that I want, but only once. And so that makes it 1 to 1. And that is from negative pi over 2 to pi over 2. Notice where on both of these, though, there's an asymptote in the middle. So there's a asymptote in the middle, so these will work, except it cannot equal, x cannot equal pi over 2 for secant, and x cannot equal 0 for cosecant. So anytime we have a 0 or a pi over 2 situation, that changes things. We're going to have to be very careful with those cases because those are undefined in the secant world. Looking at cotangent, I'm sorry, this one is actually tangent. No, cotangent. Looking at cotangent, once again, in order to get a whole section, we don't need to cut that in half. We can get a full 1 to 1 with just one period. So we're going to use this one through, this one is going to be through one full period, but it doesn't match sine like we thought it would. It doesn't even match tangent like we thought it would. That is going to be from 0 to pi, and actually it's not included on these because the asymptotes are at the edge. They are at the edge, so that's 0 to pi, just like cosine was, except of course if it's 0 or pi. So we're going to be looking at cosine anytime we use the cotangent problem.